to the IOC for the wonderful honor of giving this presentation today. And it looks like the conference has started very well, so congratulations to the local committee as well. So as Akam said, my talk today, I chose this title, New Frontiers from Old Ideas in Plasma Surface Chemistry. Of course, that's always true in science. We always are using old ideas, so maybe that's a little bit redundant. But in particular, what I'll talk about is our recent work in extending some concepts in plasma surface chemistry to look at polymers. But before I do that, I'd like to start by acknowledging the people who actually did the work. The people here listed in the upper left, Joe Bay, Dustin Ness, Ting Chung, Bill Paul, Calgary, and Monica Titus, two of whom have now left and gone to LAM, are the people who did all of the work that I'll talk about today. Joe did all of the EMD work, Dustin did a lot of the beam work, Ting did some additional recent work, Bill Paul took over from Joe, and Monica has done some of the recent plasma measurements. Some of you may know that we've had the good fortune in my group to have three retired scientists, John Cofer, Dave Fraser, and Harold Winters, who come and work with us from time to time, and they've made tremendous contributions. And I want to mention in particular the role of John Cofer in getting me into experiments, because I started life at Minnesota as a modeler. We have been working the last number of years with Gottlieb Borlein and his team in Maryland, and also Ray Funoff, Eric Hudson from Lyme Research, Cicely Anderson, D. Wang at Wilmer Haas in Grand Wilson, Texas. And I wanted to mention that in the academic year of 708, I spent at Remy in France with Eleni Mufindi and the drummer Chopin. So I had to start with this slide. Many of you have seen this, I think, and I hope, many times. This I'm calling the classic ion-neutral synergy for inorganic materials. So this paper that John and Harold wrote back in 1979 was very important in a number of ways. And in fact, it's deceptively simple. I think its power comes in part from its simplicity. If you recall, what they did was they said, okay, the plasma is very complicated. Let's see if we can understand what's going on a little bit more basically. So let's put a sample, just a silicon film on a quartz microbalance in a vacuum chamber. We can hit that surface with argon ions, some energy. And at the same time, we can expose the surface to a beam of neutral gas, in this case xenon difluoride, which decomposes quickly and spontaneously at silicon. And did a very simple experiment of measuring with the quartz microbalance the silicon etch rate as a function of time. And the famous result was that with the etch gas on only, the etch rate was relatively low, spontaneous etching does occur, but not very fast. But when they turned on the argon ion beam with the fluorine gas, the rate jumped rather dramatically. Then by turning off the xenon difluoride and only sputtering, again, the rate dropped. So the argument was quite clear that the combined effect of ions and neutrals is much greater than the sum of the other two alone. This is a nonlinear synergistic effect. So this theme we'll see again and again. One thing being the important role of ions in affecting surface chemistry, and perhaps even more importantly, the fact that those ions are acting synergetically or synergistically with neutrals. One of the consequences of the idea that you've got synergistic activities is that what typically happens is that what's important is not necessarily the flux of either the neutral, say fluorine in this case, or the ions, but in fact the ratio of those two fluxes. This happened to be something we did a couple of years ago where we compared our molecular dynamics simulations at 200 and 100 eV to some beam experiments that David Gray did in Herb Son's lab at MIT. So the silicon etch yield here is plotted as a function of this ratio, and actually in my business, this 50% difference in etch rate is considered success. I'm happy with it. We actually were a little luckier in the chlorine work that Jane Chang did. Our simulation results were kind of right on top of the measurements at 100 eV, and then we simulate 200 eV as well. The point is that although obviously real plasma chemistry, real plasma etching is a lot more complicated than argon and fluorine or argon and chlorine, a lot of key ideas can be obtained from these basic measurements that kind of frame the way we look at more complicated problems. Including, for example, if there are depositing species. I just show a result we had a couple of years ago in molecular dynamics where we were looking at the etching of silicon when there were both depositing and etching precursors. This is the profile, depth profile here, the atomic densities. this is a steady state profile. As it happens, when fluorocarbon depositing species are present, what the simulations tell us is that a layered structure forms, a fluorocarbon film a few nanometer thick is formed on the Earth's surface, and then spontaneously, we didn't make this happen, it just came out of the simulation. A silicon carbide rich layer formed below that was the silicon fluorine, disordered silicon, and then crystalline silicon. This whole thing is propagating into the silicon as the etch proceeds. Again, the key point is that the way we got this was by choosing the right ratios of the ion bombardment fluorine atoms, which are doing ultimately the etching of silicon, and the fluorocarbon precursors. In this case, it was CF. Okay, so this is a very quick overview of what we think we understand about inorganic materials, at least in the context of etching. But a few years ago, we turned our attention to the question of organic materials, and specifically polymers. And in fact, this conference has had a lot of really important work reported on polymer-plasma interactions, and I've learned a lot from this community. It is, of course, well known that polymers are susceptible to scissioning and/or cross-linking by electrons and photons. And this is kind of this thing in my title, Old Ideas. Of course, this is known very well. Indeed, electron beam and optical lithography are based on the fact that electrons and photons will affect polymers. In fact, it's even well known that plasma-generated UV, or vacuum UV, can strongly alter polymers. And the guy who perhaps most people say was the first one to point this out was Martin Hudis in 1972. And I just took a picture of his paper in Applied Polymer Science. And he basically pointed out that cross-linking polyethylene with exposure to a hydrogen low discharge, the photons from the hydrogen low discharge, was very similar to the cross-linking observed with the low-pressure mercury lamp. So the photons generated in the plasma itself were doing some interesting cross-linking polymer chemistry. And I also wanted to point out a very influential review that was published about 10 years ago by Mike Wertheimer and colleagues, in which they talked about the importance of BUV radiation in industrial processing of polymers, and showed one of the figures here looking at the BUV, particularly the BUV spectra below 200 nanometers. So these ideas are certainly well known. This is nothing new, although I would say that this community of folks who were doing plasma-polymer interactions and adhesion and so forth, that stuff wasn't that well known in the semiconductor industry, in the etching. So that, in fact, turned out to be our focus, because we work pretty closely with the semiconductor industry, and in particular, it was obvious after a while that the polymers that are virtually always used for etch masks, very little was understood about how the plasma affects those polymers. And indeed, all of these masks use plasma etched to remove materials, and so the basic question of how the mask itself is attacked by the plasma is very important. So whether we're talking about optically generated lithography for the current 193 nanometer version, different tricks that people use, or the proposed photoresist for extreme UV lithography, or recently people have looked at block die and tri-block polymers for self-assembled films, which can be exploited to make masks, or even the nanoimprint lithography masks. These are all based on polymeric materials, and after you form the pattern of the mask, you've got to etch them. So the way the plasma affects those polymers is very, very important, and little studied. So here's some cartoons about one of the issues that's currently very important in the semiconductor industry. Of course, as you know, there's this constant drive to make the future smaller and smaller. And what's happened was, especially with the new photoresists, sidewall roughening has become a very, very important problem. And there's lithography components to it and there are plasma components to it. So let me show you the litho part. This is kind of the party line. This is from a few years ago. But this view has been expressed many times. See, the idea basically is during the exposure of the light that does get into the polymer, in this case chemically amplified resist photoacid diffusion, there's a region, a transition region under the side of the mask where you're not getting full exposure. So when this region is developed, you can see the picture is there's some roughness on the sidewall. This is partly due to the fact that the polymers themselves form aggregates in their macromolecular species. So this is kind of the party line as to what is going on with so-called line edge or a line width roughness. And it's well known that this line width roughness versus line edge, line width just means they look at the total width of the line, the lower frequency roughness, if you will, down the, for example, the gate edge. And it's well established now from the device point of view that if you have high line width roughness as opposed to low line width roughness, you tend to get more leakage in the transition gate obviously that's bad. And corresponding to that, the International Technology Roadmap of Semiconductors in its 2006 update has stated